Hello everyone, in this video we are trying to follow this book Spatial Data Science with Applications in R. In this content I am trying to summarize the chapter 2 coordinates and this is going to be the quick summary, or let's say an attempt to summarize this chapter, and this might not be that helpful for any experts or any learned users. And this is just the chapter 2 and things are already getting complex. The chapter opens with the nice quote here. It says, "Data are not just numbers, they are numbers with a context. In data analysis, context provides meaning." And in the case of spatial data, we have the coordinates and the coordinate system. We have different coordinate system. Some of them might be two-dimensional and others might be three-dimensionals. And they are being referenced, or the way to represent them is in orthogonal axis or by using the distance and directions. And there can also be the time coordinates, coordinate systems. So this is the very first thing the chapter tries to tell. In 2.1 we have the quantiles units datum, and to define the quantity, it is something. It is the property of the body, phenomenon, or substance, where this property or this body or substance has some magnitude, and this magnitude can be expressed in some numbers with the reference, and by reference we mean the units of measurement or by the measurement procedure. And the measurement system can be anything that is done with the units. So we have the base units and then we have the derived units from the base units. So for instance, this meter is the base unit and the meter per second is the derived unit. There can also be the unitless measurements such as counts and the fractions. They might have some context or the meaningful use in some cases. And in many quantiles, the zero has some meaning, and the difference also gives the meaningful values. And the datum, in the case of the datum, what datum is, it is really the absolute position and the time. So it has some fixed origin from which if we go away from that point, we get the meaningful measure. So that is the datum. So it is the fixed or the absolute position and time. That is what datum is. And when the datum comes with the scale as the measurement unit here, this gives us the reference system. Then we have the ellipsoidal coordinates in 2.2. So there is some codes. We can sure go inside the codes and see line by line what each line is doing, but that is not the objective here. We can try doing this in some other context, but this code here generates this circle and some X and Y lines with numbers, and some points here is being shown. So what it is showing is that this red dot here, red line here, is the polar coordinate, and this blue one here is the Cartesian coordinates, and this is the case for the two-dimensional situation. So the Cartesian coordinates, in the Cartesian coordinates, the point is as shown here in by xy, that is 3, 4, And for the polar coordinates, we have the angle, and we have this length, or the radius in this case. So and then we have this arctan for y3, and this arctan for y3 is 0.93 radians, or 53 degree. So x, y, and r, these all have the length units, and where this phi is the angle, and this is the unitless length. And the conversion from the Cartesian to polar coordinates and vice versa can be done with some formulas. And then we have this spherical coordinates. For the case of the sphere, it's similar to the polar coordinates that we just saw, but this will be represented by three things here. The first one is the radius of the sphere, this lambda is the longitude, and this phi is the latitude. And this is the case for the spherical coordinates in the case of three-dimensional space. And here we can see some codes again, and this generates something like this here. So here, so this is the Cartesian geocentric coordinates, where only the length, where we have the three distances or three lengths, and in the ellipsoidal coordinates, which is in the right, is dealing with the angles. So just to understand two different terms here, Cartesian geocentric coordinates and the ellipsoidal coordinates. And then we can have the ellipsoidal coordinates with some values. We can have the angles measured in degrees and geocentric coordinates. And just to show how it is done in R. And we also have this one here, and this represents the parametric model for the Earth, and this is an ellipsoid with two equal semi-axis longitude. This is measured along the circle and the latitude along the ellipse. So we have some altitude on the ellipsoid, and this is the relative to the surface, approximating the mean sea level. And then we need to know which direction is positive, which direction is straight up. And the particular case is that Earth is not the perfect ellipsoid. So for this we have different ellipsoids with different shapes and parameters and bound to the Earth. And these ellipsoids are called the datums. And in the two-dimensional space, we work with the projected coordinates, and the ellipsoidal coordinates have the means that their shape, direction, areas, these are distorted when we bring them in the two dimension. And in the case of projected coordinates, we have different ways to measure the distance. So the images are not being shown here. I had tried cropping and pasting. It didn't work like that. And the distance calculation gets complicated with different types here, different types of the coordinate system, just to show that we have different lengths. And there is some concept of bounded and unbounded spaces. And then we have the coordinate reference systems, and to understand the coordinate reference systems, the chapter copies the statements or the definitions. The definitions are like this. The coordinate system is the mathematical rules. So the coordinate system is just the mathematical rules that specifies how coordinates are assigned to the points. And the datum are those parameters, or it can be also the sets of parameters that defines the position of the origin, the scale, and the orientation of the coordinate system. So this datum is trying to define or making the assumption of the shape as well. And the geodetic datum is that datum that describes the relationship of 2 or 3 dimensional coordinate system in the Earth. And the coordinate reference system is the coordinate system related to the object by the datum. And for the geodetic and the vertical datums, the object is the Earth. So these are the main points, or the main things, main agenda of the chapter. Let's say that to understand these terms. And we know that the Earth is not regular, so the surface of the Earth is irregular, and the model that fits the surface is the ellipsoid, and this gives us the datum, which may be the global or local, and the coordinates are associated with the datum, and the coordinate conversion, or there are terms as projection conversion, can be done, and these are the things in this 2.3. And then we have the 2.4. It talks about the project, and this is the package based on the C language, and it tells the history, how it came around, and tells what each development had, or each person had. And we can see that this is the way the coordinate reference systems were in the from the very beginning in the key value pairs, and this still we can see when we do these things in R. And the name letter was project 0.4, and then it started EPS registry, and then after we also had this grid raster to work with the raster data. And from 2018 there are more coordinate transformation systems. In general, what this 2.4 says is that once this development has occurred, now it's getting more easier to convert from one coordinates to other coordinates, thus making the process of coordinate transformation system more accurate and more scientific. And then we have the 2.5 WKT2, and this is the standard for encoding coordinate reference systems, so as well as transformations between the standard and format. So this is referred to as WKT2, just the way to encode these coordinate reference systems. Just for now, or for learners like us, just understanding the term will be okay, I think. And there is exercise in 2.6, just the calculations that we can do based on the formula. Just for the practice, there is numericals, and the conclusion that I can draw from this chapter is that this is very heavily packed chapter for the early learners of spatial data science, but as this is heavily packed, of course this is very important to understand so many things, and this is very useful. We need to relearn. We need to come back again and read each section very carefully, and we can check the codes. Of course, the way to generate the circles, if we are not aware about that, we can try doing with that. So this is it. So I tried to quickly go through the chapter, but this is a very big chapter. So that's all in this video. So thank you for watching.